Welcome to the Linear Integrated Circuits 555 timer experiments. This is our first design. Let the buzzer buzz for 10 seconds when the door is open. This is the circuit design of 555 timer of monostable multi-vibrator. This is RT and CT. As you already know the basics and the connections of monostable multi-vibrator, I won't explain much about it. But to aid for our application, here we have added the push to on switch. So when the push to on switch is pushed, the VCC will go directly to ground, thus the trigger will become 0, that is it will be less than VTL. Therefore at this point the output makes a transition from 0 volt to VCC and remains there for a predefined quasi state. At this point of time the capacitor charges from 0 to VTH and that point of time the buzzer will be on. Here we don't use the control voltage and this capacitor is used for stability purposes. Thus now since we need the buzzer to buzz for 10 seconds, we need to make a calculation where we need to calculate the resistance and capacitance values. So coming to the calculation part, we know that the pulse width is equal to ln VCC by VCC minus VTH into RT into CT. We know that VCC by VCC minus VTH is equal to 3 and we need the pulse width of 10 seconds. Assuming CT is equal to 47 microfarad and substituting that in the above equation, we get the resistance value as 193.42 kilo ohms. Since we don't have that type of resistance values, we'll go to the approximate standard value 200k, that is 100k in series with 100k. To help you understand better, we'll consider the output waveform too. As you can see, when the trigger goes down below VTL, the output makes a transition from 0 to VCC and stays in that quasi state for a predefined time, which is 10 seconds. And even at that moment, the capacitor charges from 0 up to VTH. So now let's move on to the practical application of this experiment.
So the circuit connections are made as shown in the previous slides. This is the 555 timer, this is the push to on switch, this is the 47 microfarad capacitor, and the capacitor here is basically used for the stability purposes. Here as you can see we have added 200k resistances in series. So now when I switch on the trigger or on the push to on switch, you will get the buzzer sound for 10 seconds.
Coming to the design 2, you need to let the LED change its color when the switch is pressed. So this is the circuit diagram of the monostable multi-vibrator. Here instead of adding the buzzer to the output, we have just added two LEDs where one terminal is connected across VCC and another terminal of this L2 is connected across ground. Initially the trigger value is above VTH, therefore the output will be at 0. Thus a potential difference is created across L1, that is this is VCC and 0. Therefore L1 turns on. When we push this push to on switch, the trigger value will be 0, that is less than VTH. Therefore the output will make a transition from 0 to VCC. Thus now a potential difference is created between this point of L2. Therefore L2 turns on, but here L1 turns off again. Now coming to the calculation part, we know the formula TPW is equal to RT into CT into ln 3. Assuming CT is equal to 47 microfarad and we need a pulse width of 10 seconds. Therefore substituting them in the above formula, we will get the resistance value as before, which is 193.42 kilo ohm. Thus we will be substituting that resistance value with the available standard resistance 200k, that is 100k plus 100k. Here you can see initially the trigger voltage is more than VTH. Thus the output will be 0 and at that moment there will be a potential difference created across L1. Thus only LED 1 is on. When the trigger voltage is less than VTL, LED will be off but L2 will be on, that is LED 2, which happens similarly for alternate cycles. Now going to the practical view of this experiment.
This is the monostable multi-vibrator circuit as explained in your slides. We have connected the output between two light emitting diodes. The positive terminal is connected here and the ground terminal is connected here. Therefore, the output is basically supplying 0 voltage and here is VCC. Thus, a potential difference has been created and this light emitting diode is on. Whenever the trigger goes below VTL, that is, when I push this switch, the output here is given as VCC and this is a ground connection. Therefore, this light emitting diode turns on, that too only for just 10 seconds. See, now again the output is giving here a ground supply or a zero voltage, thus and a potential difference is created and this is on again.
Moving on to design 3, let the LED blink with equal on and off duration with 60 blinks per minute. This is an unstable circuit. So coming to the circuit, as you already know, this is an unstable multivibrator. Here we have connected RA, RB, CT, and as we have T on is equal to T off, we have also connected a diode across RB. During charging, the capacitor charges along RA and the diode, but the capacitor discharges from RB. Here the output will be connected across to an LED. I'm sorry that we can't show it to you, but if you want to see that T on is equal to T off in a better way, connecting an LED is a better option. Moving on to the calculation part, here we need to have 60 blinks in total. Therefore, T on is equal to T off, that is T on will be of 0.5 seconds and T off will be of 0.5 seconds. As you know the formula of T on, RA into CT into ln 2. Assuming CT is equal to 100 microfarad and substituting those values to the above equation, we will get that RA is equal to 7.24 kilo ohm. Thus, as T on is equal to T off, RA is equal to RB. Considering the output waveform, the capacitor initially charges from 0 up to VTH and then it charges till VTH. The charging time constant from VTL to VTH is explained or shown as T on, and the discharging time constant from VTH to VL is considered as T off. Generally or ideally speaking, T on should be equal to T off, but here as we are also considering the diode drop for this equation, the T off is less than T on. So now moving on to the practical view of this circuit.
So here is the stable multivibrator circuit as we had shown you in your previous slides. As you can see, the LED is glowing on for 0.5 seconds and it is going off for 0.5 seconds. We have added a diode here, thus it is fulfilling its 50% duty cycle condition.
Now coming to design 4, let the LED blink for 20 seconds with on time twice of off time, that is blink 30 times a minute, only when switch is pressed. Here we will be considering both the monostable and the unstable circuits. Coming to the circuitry, this is the monostable multivibrator and this is the unstable multivibrator. The output of the monostable multivibrator is connected across to the reset pin of the unstable multivibrator, and the output of the unstable is connected across to an LED. If you have keenly observed, in the previous circuit we had connected a diode in parallel with RB, but here as we need T on to be twice that of T off, we haven't considered a diode here. So in this case, when the trigger value goes below VTL, the output of the monostable makes a transition from 0 to VCC, that is to quasi-state, for a predefined time of 20 seconds. At that point of 20 seconds, even the unstable turns on and its output makes a transition from 0 to VCC to 0. At that point of time, the LED starts blinking up to 20 seconds. So the values of RA and RB will be selected such that the value of T on will be twice of that of T off. Now moving on to the calculations part. This is the calculation of the monostable circuitry. We need to have the pulse width of 20 seconds. Therefore, considering the formula, TPW is equal to RT into CT into ln 3. Assuming CT is equal to 100 microfarad, we get our resistance value to be 181.81 kilo ohm. As we need a T on of 1.33 second and T off is equal to 0.66 second. That is, T on is twice of that of T off value. Let us assume CT to be 47 microfarad and substituting that to the T on equation of T on is equal to RA plus RB into CT into ln 2, we will get RA is equal to 20.35 kilo ohm, which is also equal to RB. Since we have not considered a diode here, the T on value will be twice of that of T off. Now coming to the output waveforms, as you can see here the trigger value is going down below VTL. At this point, the output of monostable makes a transition from 0 to VCC to its quasi-stable state for a time period of 20 seconds. At that moment, the unstable will become on, that is, it will also start to generate pulses for a time period of 20 seconds. For a time period of 20 seconds, we'll get up to 10 pulses here, as you can see. Thus, the LED will blink 10 times for that time period of 20 seconds. Moving on to the practical view of the circuitry.
So the circuit connections have been made as shown in the previous slides. This is the monostable multivibrator. Here you can see the astable multivibrator. The output from the monostable multivibrator is connected to the reset terminal of the astable multivibrator. So when I press this push to on switch, you can see the LED will blink for 10 times for 20 seconds.